Module 30, Lecture B, Inspection Displays. By the end of this lecture, you will be able to use partial dependence and ice plots to inspect fitted model behavior, compute permutation feature importance and compare it with impurity importance, and create Scikit-Learn display objects for evaluation and inspection. Dependence plots, partial dependence. Partial dependence shows how a model's predictions change as one feature changes, while averaging over the effects of other features. It is useful for interpreting complex models, such as random forests or gradient boosting. A partial dependence plot can reveal whether the relationship is increasing, decreasing, or more complex, such as home prices rising with square footage and then leveling off for very large homes. Partial dependence shows how a model's predictions change on average as one feature varies, while the other features are kept fixed. It summarizes typical model behavior across the population, not the path of any single case. For example, a model may show risk rising with age or demand falling as price increases, but individual patients, products, regions, or categories may differ. Partial dependence plots show how a model behaves, not necessarily how the real world works. They can reveal true patterns, but they may also reflect data artifacts or unrealistic feature combinations, such as changing driver age while averaging driving experience. Used carefully, they help assess whether a model is plausible, identify nonlinear effects, and communicate broad prediction trends that align with domain knowledge. Python code, partial dependence. This example shows average model behavior using partial dependence. By systematically changing one feature, the plot illustrates how the model's predicted diabetes progression responds. We set up the main tools for a regression example using Scikit-Learn. The diabetes dataset is loaded, split into training and testing data, and modeled with a random forest regressor. Matplotlib supports visualization, while partial dependence displays help show how one feature influences the model's predictions. We load the diabetes regression dataset from Scikit-Learn and return it as a pandas data frame for easier analysis. The data is then separated into input features, which contain health measurements, and a target, which contains diabetes progression values. This split prepares the dataset for training and evaluating a predictive model. The analysis focuses on the body mass index feature, called BMI. Before using it, the code checks that this feature exists in the dataset. If it is missing, an error is raised, so the analysis does not continue with invalid or incomplete data. We split the dataset into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is kept for testing, and a fixed random state ensures the split can be reproduced. This lets us evaluate how well the model performs on unseen data and how effectively it generalizes. We create a random forest regressor with 80 trees and a fixed random state for reproducible results. The model is then trained on the feature and target data, so it can learn patterns and make predictions on new inputs. The code evaluates the model on the test data using the R-squared score, which summarizes how well it predicts the target variable. It also prints the Scikit-Learn version for reproducibility, reports the rounded score, and identifies BMI as the feature being examined next. We create a Matplotlib figure as the canvas, then use Scikit-Learn's partial dependence display to show how the model's predictions change as BMI varies. The plot uses the trained model and training data, focuses on BMI, and shows the average effect of BMI on the predicted outcome. The plot is prepared by giving it a clear title, Partial Dependence for BMI, and labeling the axes to show BMI feature values and the average predicted diabetes progression. The layout is adjusted, so the title and labels fit cleanly, and then the plot is displayed for viewing. This script uses the diabetes dataset to show how a partial dependence plot can explain a model's average behavior. It trains a random forest regressor and reports its R-squared score, then focuses on body mass index. The resulting plot shows how predicted diabetes progression changes on average as body mass index varies, helping interpret how the model uses that feature. ICE plots. ICE plots show how a model's prediction for each individual observation changes as one feature is varied, while the others stay fixed. Unlike partial dependence plots, which show only an average effect, ICE plots keep the separate prediction paths visible. This helps reveal differences across cases that an average could hide, giving a more detailed view of model behavior at the individual level. ICE plots show whether a model treats a feature consistently across individual cases. When the lines are mostly parallel, the partial dependence curve is a reliable summary of the feature's average effect. When the lines diverge or cross, the feature's effect depends on other features, revealing interactions that average curves can hide, such as price affecting new and long-term users differently, or age affecting medical risk differently based on patient history. ICE plots show how a model's predictions change when one feature varies while others are held fixed, so they describe model behavior rather than real-world cause and effect. This setup can create unrealistic cases, such as changing experience without changing age. Use ICE plots as diagnostic tools to compare predictions with expectations and identify surprising patterns, ideally alongside partial dependence plots and domain knowledge. Python code. ICE plots. This script uses ICE plots to inspect a model by showing how individual predictions change. These lines can reveal differences between cases that average effects may hide. The script imports key tools for a regression workflow: NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn for machine learning. It loads the California housing dataset with synthetic regression data as a fallback, then uses a random forest regressor to model complex patterns. It also prepares partial dependence displays to show how predictions change with feature values, and splits the data into training and testing sets for fair evaluation. The process first tries to load the California housing dataset as a data frame, then samples 1,200 rows with a fixed random state for reproducibility. It identifies the feature names and uses median house value as the target, while checking that the sample has the expected size and target column. If loading or validation fails, it switches to synthetic regression data with 1,200 samples, 6 features, and added noise, using generic feature names instead. The setup first checks whether the real housing dataset was loaded. If it is available, it uses the dataset's feature columns and median house value target, with median income chosen for the individual conditional expectation plot. If not, it falls back to generated regression data, using its features and target values, and selecting the first feature for the plot. This ensures the regression task has the needed inputs, no matter which dataset is used. We split the dataset into training and testing parts using Scikit-Learn's train-test-split function. 25% of the data is kept for testing, so the model can be evaluated on examples it did not see during training. A fixed random state makes the split reproducible, helping us measure how well the model generalizes to new data. A random forest regressor is created with 60 decision trees, each limited to a depth of 5, and a fixed random state for reproducible results. The model is then trained on the feature and target data, so it can learn their relationships, including nonlinear patterns. We select the first 80 rows from the test data to inspect the model's predictions. Before running the individual conditional expectation analysis, we confirm that this subset is not empty. If it has no observations, an error is raised because the inspection requires at least one data point. The script reports the Scikit-Learn version to confirm the working environment, then identifies the feature used in the individual conditional expectation plot. It also explains that each thin line represents one test observation, showing how individual predictions change for that feature rather than only an overall average effect. This code sets up a Matplotlib plotting area, then uses Scikit-Learn to create an individual conditional expectation plot for a trained model. The plot shows how predictions change for individual test observations as one selected feature varies. To keep the visualization readable, it displays a random subsample of 40 observations and uses a fixed random state for reproducibility. The code finishes the ICE plot by adding a clear title, labeling the feature on the horizontal axis, and labeling the predicted target values on the vertical axis. It then displays the plot so the individual prediction responses can be inspected. This script creates individual conditional expectation plots to examine how a random forest regressor makes predictions. It uses the California housing dataset when available, or synthetic data as a backup, then trains the model and plots how predictions change as one feature varies. Each thin line represents one observation, helping show individual response patterns that average effects can hide. Computation methods. A partial dependence plot shows how a model's predictions change on average when one or a few features are set to different values while the other features stay the same. The model makes predictions on these modified data, and the averaged results form the plot. For example, a bank could vary applicant income to see how predicted credit risk changes, helping analysts understand whether higher income lowers risk consistently or in a more complex way. ICE plots show how a model's prediction changes for each individual observation as one feature varies. Unlike average plots, they can reveal differences across cases, such as when people respond differently to age or discounts. This makes them useful for spotting hidden variation and interactions that a single overall trend may miss. Dependence plots show how a model's predictions change as input features vary, but they must be interpreted carefully. Continuous features should be evaluated within the observed data range, while categorical features are checked by category. Avoid unrealistic feature combinations because they can create misleading extrapolations. Treat these plots as tools for inspecting model behavior, not as evidence of causation, and interpret them with domain knowledge and awareness of feature correlations. Python code, computation methods. This script shows how partial dependence is computed and interpreted. It uses ICE curves to display how individual predictions change, then compares those individual effects with the average effect. The script imports the main tools needed for a regression workflow. It uses NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn tools to create synthetic regression data, split it into training and testing sets, train a decision tree regressor, and visualize partial dependence. It also imports Scikit-Learn itself, so the script can check the library version. A synthetic regression dataset is created with Scikit-Learn's makeRegression function to test regression models in a controlled setting. It includes 300 samples with 4 features, plus added noise to reflect real-world variability. A fixed random state ensures the same dataset is produced each time the code runs. The code first verifies that the feature's data has the expected size, 300 rows and 4 columns. If it does not, it raises an error to signal the mismatch. This check helps catch data structure problems before model training and evaluation begin. The dataset is split into training and testing parts using Scikit-Learn's train-test-split function. 25% of the data is kept for testing, so the model can be evaluated on data it has not seen before. A random state of 42 makes the split reproducible each time the code runs. We create a simple decision tree regressor with a limited depth and a fixed random state for reproducible results. After training it on the feature and target data, the model can be used to examine how well it captures the relationship between inputs and the target. This also prepares the model for later analysis with partial dependence plots. The model is evaluated on test data using the R-squared score, giving a quick measure of how well it predicts the target values. The Scikit-Learn version is also reported to support reproducibility, and the score is rounded for readability. The inspection then focuses on feature 0, using individual conditional expectation curves and their average to show how that feature influences the model's predictions. A Matplotlib figure and axes are created to hold the visualization. Scikit-Learn's partial dependence display is then used with the trained model and test features to examine feature 0. The plot shows both individual conditional expectation curves and the average partial dependence, using a limited sample of 40 for clarity and a fixed random state for reproducibility. The code prepares the plot for interpretation by adding a title, labeling the horizontal axis as feature 0 values, and labeling the vertical axis as predicted target values. It then displays the visualization so the ICE curves and their average partial dependence can be examined. This script shows how to use a decision tree regressor to study partial dependence. It creates a synthetic regression dataset, trains and evaluates the model, then focuses on the first feature. Using Scikit-Learn's partial dependence display, it plots both individual conditional expectation curves and their average to show how changes in that feature influence the model's predictions. Feature importance. Permutation importance. Permutation importance measures how much a trained model's performance worsens when one feature is randomly shuffled. Shuffling breaks that feature's connection to the target, while keeping its overall distribution the same. A large performance drop means the feature is important, while little change suggests the model does not depend on it much. This approach judges importance by predictive impact, rather than by inspecting the model's internal structure. Permutation importance is a model-agnostic way to measure how much each feature affects predictive performance by disrupting that feature and observing the change in results. It can be used across many model types, including tree-based models, linear models, support vector machines, neural networks, and ensembles. Because feature importance can depend on the evaluation metric and the data, results should be interpreted in the context of the specific task. Permutation importance estimates how much a model depends on each feature by repeatedly shuffling that feature and measuring the drop in performance. Repeating the shuffle reduces the effect of random chance, but the result shows association with model performance, not causation. For reliable estimates, use validation or test data rather than training data. Used carefully, it helps explain and compare which features matter most to the model. Python code. Permutation importance. This example compares two ways to measure feature importance. Permutation importance shows how much test performance drops when a feature is disrupted, helping reveal which features the model relies on most. We import key Python libraries for a machine learning workflow: NumPy for numerical operations, Matplotlib for plotting, and Scikit-Learn for datasets and models. We then load Scikit-Learn's breast cancer dataset, a standard classification dataset, to train and evaluate a machine learning model. We import key Scikit-Learn tools for building and evaluating a classification model. The random forest classifier combines many decision trees to improve accuracy and reduce overfitting, while permutation importance estimates which features matter most by checking how shuffling each one affects performance. We also use a train test split to evaluate the model on unseen data, and an accuracy scoring function to compare predictions with the true labels. We load Scikit-Learn's breast cancer dataset, a common benchmark for classification models. The dataset's features are stored as the model inputs, and the feature names are also saved so the inputs can be understood and interpreted later, such as when reviewing model results or feature importance. First, the target values are separated from the dataset, so the model knows what it is trying to predict. Then the number of feature rows is checked against the number of target values. If they do not match, an error is raised to ensure every set of features has a corresponding label for reliable training and evaluation. The dataset is split into training and testing sets using Scikit-Learn's train test split function, with 30% reserved for testing. Stratification keeps the class proportions the same as in the original data, helping maintain balanced representation. A random state of 42 makes the split reproducible across runs. A random forest classifier is created with 80 trees, each limited to a depth of 5, and a fixed random state for consistent results. It is then trained on the feature data and target labels, so it can learn patterns and later make predictions on new data. We first measure the model's baseline accuracy on the test data by comparing its predicted labels with the true labels using Scikit-Learn's accuracy score. This shows how well the model performs before any feature shuffling. We also report the Scikit-Learn version for reproducibility, then print the test accuracy rounded to 3 decimal places. Permutation importance is calculated on the test data using Scikit-Learn to see how much model accuracy drops when each feature is randomly shuffled. The trained model, test features, and test labels are used, with repeated shuffling and a fixed random state for stable, reproducible results. Features that cause the largest accuracy drop are the most important for the model's predictions. To identify the 5 most important features, we sort the permutation importance scores and select the highest 5. We then use their positions to find the matching feature names and their permutation importance values. Finally, we retrieve the model's impurity-based importance scores for the same features so the 2 importance measures can be compared. To prepare a feature importance plot, we assign each selected feature a position so the bars can be placed correctly. We choose a consistent bar width, then create a Matplotlib figure and axis with a 9 by 5 inch canvas. This setup allows the feature importance values to be displayed side by side clearly. The chart compares permutation importance and impurity importance using horizontal bars. Each feature gets 2 bars placed side by slightly offsetting their vertical positions, making the 2 importance measures easy to compare. The y-axis labels are then aligned with the bars and named with the selected features, so the chart is clear and interpretable. The plot is formatted to compare permutation importance with impurity importance. The horizontal axis shows importance values, while the vertical axis lists the features. A clear title, legend, and adjusted spacing make the chart easier to read, and the plot is then displayed. This script compares 2 ways to measure feature importance in a random forest model, using the breast cancer dataset. After splitting the data, it trains the model and checks its test accuracy as a baseline. It then compares permutation importance, which measures how accuracy changes when each feature is shuffled, with the model's built-in impurity-based importance. The top 5 features are plotted side by side to show which inputs the model relies on most for its predictions. Correlated feature effects. Feature importance is harder to interpret when features are correlated, because one feature can stand in for another. Permutation importance measures how much performance drops when a feature is shuffled. But with overlapping features, this drop may look small, even if the feature is useful. For example, in a housing model, shuffling square footage may matter less if the number of rooms still provides similar information. So a low permutation importance score may reflect limited unique contribution, not true unimportance. When features are correlated, as often happens in healthcare or finance, permutation importance can be harder to interpret. If one feature is shuffled, but related features still carry similar information, the model's performance may not drop much, making that feature seem less important. But if the feature captures unique information, shuffling it can strongly reduce performance. So permutation importance shows how much the model depends on a feature, not the feature's absolute real-world value. When interpreting feature importance, consider related features as a group, rather than judging each one alone. Correlated inputs may share information, so a feature with low permutation importance can still contribute to the model's overall pattern. Feature importance should therefore be used as a guide, checked against domain knowledge and other tools, not treated as a complete explanation. Python code. Correlated feature effects. When predictors share information, compare their importance carefully. Correlation can make a model's reliance on one feature less obvious, because importance may be split across related predictors. The resulting patterns help reveal how shared information affects feature importance. We import the main tools needed for a machine learning workflow: NumPy for numerical work, Matplotlib for visualization, and Scikit-Learn for modeling and evaluation. From Scikit-Learn, we use a random forest regressor for prediction, permutation importance to measure feature influence, the R-squared score to assess performance, and train test splitting to evaluate the model on unseen data. A reproducible random number generator is created with a fixed seed of 42. The dataset size is set to 800 samples, and a normally distributed random signal of that length is generated. This signal provides the base for building correlated features. Two new features are created by adding a small amount of random normal noise to the original signal, so they remain closely correlated with it while having slight variation. A third feature is generated as independent random noise, providing a control for comparing how unrelated information affects model performance. The target variable is created from the signal, scaled by 5, with added random noise to mimic real-world variability. The feature matrix then combines correlated feature A, correlated feature B, and a noise feature as columns for model training. Feature names are also assigned, so the variables can be identified during analysis and visualization. Before modeling, the code confirms that the dataset has the expected shape, 800 samples and 3 features. If the dimensions are wrong, it raises an error to stop the process. This check helps ensure the data is properly formatted for training and testing the model. The dataset is split into training and testing parts, so the model can be evaluated on data it has not seen before. Using Scikit-Learn's train test split function, 30% of the data is reserved for testing, while a fixed random state makes the split reproducible. The result is separate training and testing data for both the features and the target, ready for the next modeling steps. We create a random forest regressor with 80 trees and a fixed random state, so results can be reproduced. After training it on the feature and target data, the model learns patterns for making predictions. Its built-in impurity importance can then indicate which features most influence those predictions. Permutation importance measures how much each feature affects a model's performance. It does this by shuffling one feature at a time and checking how much the model's accuracy drops. Using Scikit-Learn, we apply this to the trained model and test data. with repeated shuffles and a fixed random state for reliable, reproducible results. Features that cause larger performance drops are considered more important. The code evaluates the model by calculating the R-squared score on the test data, showing how closely its predictions match the actual values. It also reports the Scikit-Learn version for reproducibility, prints the score rounded to 3 decimal places, and notes that correlated features can share predictive credit, which can affect how model results are interpreted. To prepare the bar chart, we assign each feature a position along the x-axis so the bars line up correctly. We then choose a bar width of 0.35 and create a 7 by 4 inch plotting area with Matplotlib to display the feature importance scores. The code creates a side-by-side bar chart comparing 2 feature importance measures for a random forest model. One set of bars shows impurity importance, while the other shows permutation importance, which reflects how much performance drops when a feature is shuffled. Placing the bars next to each feature makes it easier to see how the 2 methods assign predictive credit. The plot is titled Correlated Features Split Importance, to show that it compares feature importance for correlated features. The x-axis lists the dataset features, and the y-axis shows each feature's importance score. The feature labels are aligned with their bars, and the legend distinguishes the importance types being compared, such as impurity and permutation importance. Adjusting the layout makes sure the plot elements fit cleanly without overlapping or cutting off labels and titles. Displaying the plot then shows the feature importance scores as bar charts, making it easier to compare impurity importance and permutation importance for correlated features. This script shows how correlated features can distort feature importance in a machine learning model. It trains a random forest regressor on data with 1 true signal, 2 correlated features, and 1 noise feature, then reports its R-squared score on unseen data. It compares impurity-based importance with permutation importance to show that correlated features can split predictive credit, making individual importance scores harder to interpret. Impurity importance comparison. Impurity importance measures which features a tree-based model relies on by totaling how much each feature improves split purity during training. Features used often in helpful splits receive higher scores, making the method fast and common in decision trees and random forests. However, it reflects how the model was built on training data, not how much each feature improves predictions on new data. Permutation importance measures how much a model's validation performance changes when one feature is shuffled, breaking its relationship with the target while leaving the model unchanged. A large drop in accuracy or increase in error means the feature is important. This approach reflects real predictive impact, so a feature that looks important by tree impurity may matter less in practice, while a less obvious feature may still be valuable through interactions or specific parts of the data. Impurity importance and permutation importance offer different views of how a model uses features. Impurity importance can overvalue features with many possible splits, while permutation importance better reflects predictive reliance, but can be misleading when features are correlated. Use them together. Agreement increases confidence, and disagreement signals the need to check feature distributions, correlations, and validation performance. Python code, impurity importance comparison. Tree feature importance can be measured in 2 main ways. Impurity-based importance looks at how much each feature improves splits during training, while permutation importance checks how much held-out performance drops when a feature is disrupted. We import key Python libraries for a machine learning workflow, NumPy and Pandas for data handling, Matplotlib for visualization, and Scikit-Learn for modeling and evaluation. The breast cancer dataset from Scikit-Learn is loaded as a classification example. A random forest classifier is used to build the model, while permutation importance measures how much each feature affects accuracy when its values are shuffled. The data is split into training and testing sets, so performance can be evaluated on unseen data. We load Scikit-Learn's breast cancer classification dataset for demonstration and analysis. The dataset is separated into feature data and target labels, and the feature names are saved in a convenient array. This prepares the data for exploring which features matter in classification. To simplify the example, we choose a small set of important features, such as mean radius and mean texture. We then find where those features appear in the full feature list and keep only the matching columns in the feature matrix. This reduces the dataset to the features we want to analyze. We verify that the feature matrix has the same number of columns as the selected feature names. If they do not match, an error is raised to signal that feature selection produced unexpected results. This check helps catch problems early and prevents later analysis errors. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function. 30% of the data is reserved for testing, while stratification keeps the class distribution consistent in both sets. A fixed random state makes the split reproducible across runs. We create a random forest classifier with 80 trees and a maximum depth of 4 to balance performance and complexity. A fixed random state makes the results reproducible. The model is then trained on the input features and labels, so it can learn patterns and make predictions on new data. Permutation importance measures how much a model's performance drops when each feature's values are randomly shuffled in the test data. Repeating the shuffling 10 times makes the estimate more stable, and using a fixed random state makes the results reproducible. Features that cause a larger drop in accuracy when disrupted are considered more important. We create a pandas data frame to compare feature importance scores from a random forest model. It stores each selected feature along with its impurity-based importance and its permutation importance. Sorting the data by permutation importance from highest to lowest makes it easier to identify and visualize the most influential features. The code first reports the Scikit-Learn version to support reproducibility, then measures the trained model's test accuracy rounded to 3 decimal places. It also identifies the most important feature using impurity importance, showing which feature most reduces uncertainty in the model. Finally, it finds the top feature by permutation importance, showing which feature most affects performance when its values are shuffled. Set up a Matplotlib plot with an 8 by 4 inch figure and an axis. Then create bar positions based on the number of features in the importance table, and choose a bar width of 0.38 so the bars are spaced clearly on the x-axis. A bar chart compares feature importance using 2 methods, impurity importance and permutation importance. The 2 sets of bars are placed side by side for each feature, with one shifted slightly left and the other slightly right, so they are easy to distinguish. This layout makes it simple to compare how each method ranks the importance of the same features. The plot is formatted to compare impurity-based and permutation feature importance. It includes a clear title, labels the features on the x-axis and importance scores on the y-axis, and aligns each feature name with its tick mark for readability. A legend identifies the 2 importance methods, making the comparison easier to interpret. The layout adjustment makes sure the plot elements fit cleanly without overlapping or being cut off. Then, the display command shows the plot, letting you compare feature importance from impurity-based and permutation-based methods. This script compares two ways to measure feature importance in a random forest classifier using the breast cancer dataset. After training and testing the model on selected features, it reports test accuracy and compares impurity-based importance with permutation importance, which measures how much performance drops when each feature is shuffled. The output includes the Scikit-Learn version, the top feature from each method, and a visual comparison showing that the two approaches can reg feature significance differently. Display objects. Display basics. In Scikit-Learn, display objects help create and reuse visual summaries of a model's behavior and performance. They connect the fitted model, evaluation data, and plot elements, making it easier to inspect results, compare models, and adjust visual details. This makes visualization a practical tool for judging model trustworthiness and interpretability. Display objects in Scikit-Learn make it easier to create and customize evaluation plots from model results. They turn raw predictions and numerical outputs into visuals that support interpretation, discussion, and auditing. This helps analysts assess model performance and use those insights in broader evaluation workflows. Display objects in Scikit-Learn make model inspection more reproducible and modular by separating evaluation from presentation. This lets analysts create consistent visuals, refine them without changing the underlying logic, and share clearer evidence with different stakeholders. The result is a more reliable workflow for reviewing and updating model results. Python code. Display basics. This example creates a Scikit-Learn display object, which stores a plot so it can be customized later. The output is a labeled confusion matrix. We import the main tools needed to build and visualize a simple classification model. Matplotlib supports plotting, Scikit-Learn provides machine learning utilities, and the iris dataset supplies sample flower data. We also use tools for showing decision boundaries, creating a logistic regression classifier, and splitting the data into training and testing sets for proper evaluation. We load the iris dataset from Scikit-Learn, a common beginner dataset with flower measurements. To keep the visualization simple, we use only the first two features, usually sepal length and sepal width, and store the species labels separately. This prepares the data for basic visualization and modeling. The code verifies that the feature data and target labels have the same number of entries, so each example has a matching label. If they do not match, it raises an error to signal that the dataset is inconsistent and must be fixed before training. The dataset is divided into training and testing parts so the model can be evaluated fairly. Scikit-Learn's train-test-split function separates the features and labels into these sets, while stratification keeps the class proportions the same as in the original data. A fixed random state makes the split reproducible, producing training and testing data ready for model building and evaluation. We create a logistic regression classifier and set it up to converge reliably and give reproducible results. The model is then trained on the training data, allowing it to learn patterns that it can use to make predictions on new data. We use Scikit-Learn's decision boundary display to visualize a fitted logistic regression model on the test data. The display shows the model's predicted classes, with a semi-transparent boundary, so the class separation is easier to see. This helps assess how well the model distinguishes the different classes. Add the test data points to the decision boundary plot using a scatter plot, coloring each point by its true class label to help assess model performance. Then, label the horizontal and vertical axes with the names of the two features so the plot is easy to interpret. The code labels the plot to show that the decision boundary display stores both the figure and axes, then prints the Scikit-Learn version for reproducibility. It also checks the display object type and confirms the stored axes title was set correctly. Finally, it shows the plot so the decision boundary and test data points can be inspected visually. This script shows how to visualize a logistic regression decision boundary with Scikit-Learn display objects. It uses two features from the iris dataset, splits the data for training and testing, trains the model, and plots the decision regions with the test points colored by their true labels. The display object stores the figure and axes so the plot can be customized, including feature labels and a title. The script also prints basic setup information, such as the Scikit-Learn version, the display object type, and the stored axes title. Classification displays. Scikit-Learn classification displays turn model evaluation results into clear visual summaries by keeping key information, such as the fitted model and predictions, in one place. They are useful when classification performance cannot be judged by a single metric, such as in spam detection or medical diagnosis. These displays help analysts see prediction patterns, errors, and threshold effects, making model performance easier to interpret and compare. A confusion matrix display helps evaluate classification models by comparing predicted classes with the true classes and making errors easy to spot. It can show, for example, when one type of request or diagnosis is being confused with another. This makes it useful for data scientists finding model weaknesses and for project managers judging reliability. Because it fits into the model evaluation workflow, it is more structured and reusable than creating plots manually. In classification, probability scores are useful because different thresholds can change the balance between errors. Receiver operating characteristic and precision recall displays show these trade-offs, helping teams compare classifiers and choose settings that match their goals, such as catching more fraud or avoiding irrelevant recommendations. Scikit-Learn display objects make these plots consistent and easy to update for reports and real-world decisions. Python code, classification displays. This example creates a classification display that uses a confusion matrix to show where the model makes errors. The plot presents the stored display information in a clear visual form. We set up the main tools for building and evaluating a simple classification model on the iris dataset. Matplotlib supports visualization, while Scikit-Learn provides the dataset, logistic regression model, train test splitting, feature scaling, and a pipeline to combine pre-processing with training. A confusion matrix display is also imported to help visualize how well the model performs. We load the iris dataset from Scikit-Learn, a standard dataset for classification. It contains flower measurements as features and species labels as targets, preparing the data for later processing and model training. Before training, the code verifies that the feature data and target labels have the same number of rows. This confirms that every data point has a matching label. If the counts differ, it raises an error to prevent incorrect model training. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function. 30% of the data is kept for testing, while stratification preserves the original class proportions in both sets. A random state of 42 makes the split reproducible each time the code runs. A machine learning pipeline combines feature scaling with logistic regression classification. The scaler normalizes the training features, and the classifier is trained with fixed settings for consistency. Fitting the full pipeline only on the training data helps avoid data leakage and supports better performance on new data. The model's test accuracy is measured using the score method, which reports the average accuracy on unseen data. The Scikit-Learn version is also printed to support reproducibility and compatibility. Finally, the test accuracy is shown rounded to 3 decimal places for a clear summary of performance. We create a confusion matrix display from the trained model using the test features and test labels. The iris target names are used as display labels, so the results are easier to interpret. And a blue color map helps distinguish the matrix values visually. The code checks a Scikit-Learn confusion matrix display by printing the display object's type and the shape of its stored confusion matrix. This confirms that the display was created correctly and that the matrix dimensions match the expected number of classes. The confusion matrix plot is finalized by adding a title for the iris dataset, labeling the horizontal axis as predicted classes and the vertical axis as true classes, then using Matplotlib's show function to display the visualization. This script trains a simple iris flower classifier by splitting the data into balanced training and test sets, scaling the features, and fitting a logistic regression model. It reports the model's test accuracy as a quick performance check. It also displays a blue confusion matrix, showing how the true classes compare with the predicted classes, so prediction errors are easy to spot. Regression display tools. Scikit-Learn's regression display tools help evaluate models that predict continuous values by combining plots, computed results, and reusable display objects. They make it easier to see whether predictions match observed values and whether residuals reveal patterns that average error scores might hide. By using these displays on separate evaluation data, you can better inspect and communicate where a regression model performs well or misses important structure. Prediction error and residual displays help evaluate how well a model's predictions match real outcomes. Points close to the reference line suggest accurate predictions, while clear departures can reveal bias or missing relationships. Residual patterns show whether errors are random or systematic, such as a model performing well for typical cases, but poorly for high-end properties or peak sales periods. Regression display objects in Scikit-Learn provide a consistent way to visualize and compare model performance. They can be built from estimators, predictions, or saved results, so plots stay tied to the actual data and model outputs rather than manual charting. This makes comparisons across models more reproducible and helps communicate where predictions are reliable, even to non-technical audiences. Python code, regression display tools. This example creates a regression display that compares predicted values with the true values. The resulting plot gives a quick visual sense of how well the model fits the data. We import the main tools needed to build and evaluate a simple linear regression model. Matplotlib is used for plotting. Scikit-Learn provides the machine learning utilities, and the diabetes dataset supplies the data. We also bring in linear regression, a prediction error display for comparing predictions with actual values, and a train test split tool to evaluate the model on separate data. We load Scikit-Learn's diabetes dataset, a ready-made dataset for regression. It includes input features describing diabetes-related attributes and target values representing the progression measure to predict. This makes it a convenient real-world dataset for testing regression models without manual data collection or pre-processing. The code first verifies that the feature data and target values have the same number of entries. This confirms that each feature set matches one target value. If they do not match, it raises an error to warn that the data is misaligned and cannot be used correctly for training. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function. 75% of the data is used to train the model, while 25% is kept for testing. A fixed random state of 42 makes the split reproducible, and the test set helps evaluate how well the model performs on unseen data. We create a Scikit-Learn linear regression model and train it using the training features and target values. During training, the model finds the best fit line that reduces the difference between predicted and actual values. This lets it learn the relationship in the data so it can make predictions on new examples. The code evaluates the model by calculating its R-squared score on the test data, where a value closer to 1 means the predictions fit the actual results better. It also prints the Scikit-Learn version for reproducibility, then reports the rounded score as a concise measure of test performance. We use Scikit-Learn's prediction error display to compare a trained model's predictions with the true test values. By creating the display from the estimator and choosing an actual versus predicted view, we can quickly see how closely the predictions match the real data. The plot is customized by adding a clear title and labeling the axes to compare actual and predicted diabetes progression values. The x-axis shows the true values, while the y-axis shows the model's predictions. Displaying the plot lets us visually assess how closely the predictions match the real outcomes. This script trains a linear regression model on a diabetes dataset after splitting the data into training and test sets. It evaluates the model with the R-squared score on the test data, then shows a prediction error plot comparing actual diabetes progression with predicted values. The plot helps indicate how closely the model's predictions match the real outcomes. In this lecture, you learned to use partial dependence and ICE plots to inspect fitted model behavior, compute permutation feature importance and compare it with impurity importance, and create Scikit-Learn display objects for evaluation and inspection. In the next module, Module 31, we will go over computing parallelism.
Thank you for your attention. See you all in the next lecture.